If I got a roller coaster and that roller coaster has a car, let's say at the top of the hill at rest, let's say V is equal to 0 meters per second, and that car rolls down the hill in a frictionless system. So let's assume that there is no friction on this. The reality is that's never going to be true. There's always going to be friction. But just like most of our problems so far, we're going to ignore friction. Gets to the bottom of the hill. We want to find out maybe how fast that car is moving when it reaches the bottom of the hill, if the hill happens to be, say, 50 meters high. How to go about doing that? Well, there's a couple of ways, but the one way that I want to show you today to go about doing this is using a law that we call the law of conservation of energy. And the law of conservation of energy, as we briefly alluded to yesterday, tells us basically that the total energy in a system is going to remain the same. So you can have the energy of an individual object going up or down. We can have the energy changing from one type to another, but the total energy in the system, which will account for everything, is going to remain the same. What do we have up at the top here? Well, we've got potential energy. That potential energy, as it goes down the hill, is going to decrease. We're going to have less potential energy than we have when we start. But as it goes down the hill, if potential energy decreases, then kinetic energy is going to increase. So EP, as it goes down the hill, goes down. EK, as it goes down the hill, goes up. The total mechanical energy, which is the sum of kinetic and potential energy, is going to remain the same. So let's say you have 20 joules of potential energy at the beginning. How many joules of kinetic energy do we have at the end? Yep, 20 joules. If we go halfway down, how much potential energy do we have halfway down? Yep. We've got 10 joules of potential energy and 10 joules of kinetic energy. If we go 3/4 of the way down, then we only have 5 joules of potential energy left, and we'd have 15 joules of kinetic energy. So what we're saying here is the energy at any 2 points, this point and this point, this point and this point, any 2 points along this path, if we're accounting for all the energy, the total mechanical energy, the sum of kinetic and potential is going to remain the same. Okay, we mentioned this yesterday that when we go on our field trip to West Edmonton Mall on the 30th or the 31st of May, we're going to use this a lot, this whole idea of the law of conservation of energy. Okay, remember that. The energy at any 2 points in the absence of friction is going to remain the same. All right, I'm going to give you a few notes here, and then we'll give you some examples. First thing is literally just a statement of the law of conservation of mechanical energy. Energy can't be created and it can't be destroyed. It can be transformed from one kind to another. Okay, you saw in the example that I just gave you that potential energy is converted to kinetic energy as it goes down the hill. If we're going up a hill, then we start with kinetic energy, right? If you got a car that's trying to roll up the hill, not under its own power, but under just because it had inertia, just because it was moving, then you have to have kinetic energy at the bottom of the hill, and you've got to have potential energy at the top of the hill. So in that case, it would be kinetic that decreases and potential that increases. But the total is going to remain the same again at any 2 points, top and bottom, middle, 3/4 of the way up, 3/4 of the way down, and so on. Sorry, not yet. Now, sometimes there's energy added to a system. Now, when we say energy is added to the system, that doesn't mean that it's created. If there's a wind blowing that causes something to speed up more than just gravity, then the total amount of energy is still conserved. The total amount of energy still stays the same if we account for all the energy. If we account for the kinetic energy of the wind before it interacts, then the total amount of energy will stay the same. Understand though, even if we do add energy in and we have a tough time accounting for it, and we have a tough time turning it into a math problem that we're going to see in a few minutes, energy still wasn't created. It never is. Similarly, sometimes it looks like energy is taken away. Sometimes it looks like energy is destroyed, but it's not. You're driving down the highway in your car, and a deer runs out in front of you, and you slam on your brakes, and you come to a stop. Hey, energy wasn't conserved, right? Energy was destroyed. You had a certain amount of kinetic energy in your car, and now you have nothing. because you're stopped just short of hitting a deer. Energy was destroyed, but it wasn't destroyed. It was just converted to something else. If you were to go outside your car right after that happened and touch your tires would be warm. Why? Because the kinetic energy of the car was converted to thermal energy in your tires, heat in your tires. It wasn't destroyed, it was just converted to another form. If we account for all the types of energy, including kinetic potential and maybe even thermal energy in your tires, then you would see that the energy remains the same. It's never created. It's never destroyed. That is the law of conservation of mechanical energy. Now, problems that we're going to do in Physics 20 are going to involve situations where it's fairly easy to account for everything. So we're not adding energy to the system. We're not taking energy away from the system. It's just the energy that is in it in the beginning is the energy that's in it at the end, like the roller coaster problem that I showed you a minute ago. Those are the kinds of things we're going to do in Physics 30. If that's the case, then we're simply going to say mathematically the law of conservation of energy can be stated this way: EI equals EF. The initial energy equals the final energy. Now, remember, we can define the initial point and the final point wherever we want. Okay, the initial point could be the car at the top of the hill. It could be the bottom. It could be the energy of the car somewhere in between. The final energy of the car could have been top, bottom, or somewhere in between. We can define our 2 points wherever we want. I hesitate to even call them initial and final. What we're saying here is the energy at any 2 points is equal. The total mechanical, total potential, and kinetic energy at any 2 points in the absence of outside forces is going to remain exactly the same. We're going to do an example, a relatively straightforward example. It doesn't look like a roller coaster problem at all, but in the end, it ends up being solved the same way as that example that we gave you a few minutes ago and didn't solve. It says a 500-gram ball was thrown downward at a speed of 5 meters per second from a height of 35 meters. The speed of the ball when it hits the ground. So we're assuming that the ball is thrown straight down, but in the end, it doesn't really matter. It's thrown straight down, it's thrown down at an angle. It doesn't really matter. Kinetic energy, potential energy are both scalars. The direction doesn't matter. We can analyze this problem using conservation of energy regardless of whether it was thrown straight down or at an angle. We don't have to worry about including any angles or resolving any funny angles or anything like that. So whether it goes straight down like this or whether it happens to be on a track like the roller coaster and goes down like this, if it starts moving at 5 meters per second, then the speed at the bottom will be exactly the same regardless of which path that it took. So how are we going to go about solving this question now? Well, let's write down some givens. We know that the law of conservation of mechanical energy applies. The height is changing, right? Basically, anytime you have a problem where the height is changing, the law of conservation of energy is applicable. It doesn't mean it's the only way to solve the problem, okay, but it means it's applicable. There's another way to solve this problem that probably a lot of you are thinking of right now, and it works. If we did it this way back in Unit 1, it still works. But this is just another way now, another tool in the toolbox that you can solve this problem with. Okay, we got a mass of 500 grams. We're going to make that kilograms. We're going to say the initial speed is 5.00 meters per second. We don't know what direction that is, so we'll just make it speed, not velocity. The height is 35 meters. That's the initial height, 35.0 meters. And we want to find the speed as it reaches the ground. In other words, we want to find VF. If we're going to solve this using conservation of mechanical energy, then we'll say EI equals EF. Now, here's the strategy once you get into this. You got to ask yourself at this point, what kind of energy does this ball have before, as it's being thrown downward? So in other words, after it's released from the hand, but before it starts actually going downwards, what kind of energy does it have? Give me one kind of energy that it has. What's one kind, Jenna? It's got potential energy, right, because it's got a height. So let's say MGH initial, because it's got a height. If it's a If it's above our reference point, which in this case is probably going to be the ground, then it's going to have gravitational potential energy. Is there anything else that it has, or is that it? Rosie? It does have kinetic because it's moving at a speed of 5 meters per second. Downward, upward, doesn't really matter. It's moving at 5 meters per second. So we're going to say it's got potential and kinetic energy at the beginning. Now, if this was just dropped, right, we take the ball and we just drop it, then the initial speed would be 0, and therefore the initial kinetic energy would be 0. We just say, as Gianna said, that it's potential energy in that case. But here, because it's got a height and because it's moving, it's got kinetic and potential energy. What's the speed of the ball as it hits the ground? Not after it hits the ground, but as it hits the ground, it's moving. Right? I think we did back in Unit 1 a little demonstration to show you how to recognize that there is a speed of an object when it hits the ground. We made somebody lay down on the floor at the front. Who was that? Okay, we made Dylan lay down on the floor at the front, and we threatened to drop a hole puncher on him. Of course, we weren't going to drop it, right? But in the end, it was going to hurt, right, Dylan? It was going to hurt because when it hits, it's moving. Now, after it hits, it's not moving. But when it hits, it's moving. Therefore, the final energy here, as it's moving when it hits the ground, what kind is it going to have? It's moving, it's got to have kinetic, right? We'll call that 1/2 mvf squared. Does it have potential when it hits the ground? Kristen, does it have potential energy when it hits the ground? No, because it doesn't have a height anymore, right? Now, if we said, how fast is it moving halfway down, then we would say it has kinetic and potential energy, right? But when it hits the ground, it doesn't have a height anymore, so it doesn't have any potential energy. Oh, I see a little bit of a shortcut here. Does anybody spot it? Save myself a tiny little bit of work on my calculator. You don't have to spot this. It works even if you don't spot this shortcut. But I just caught this. M is the same, and it appears in every term. That means it cancels out. The fact that it appears twice on the left side doesn't matter. If you can divide every term by M and have it cancel, then it cancels out of all of them. G, we're going to say, is 9.81. HI is 35 meters, plus 1/2 VI squared, 1/2 of 5 squared. By the way, in this one, we're probably not going to rearrange it before we plug in our numbers. It just gets a little bit too ugly. Let's solve this now. Let's say 9.81 times 35. I get 343.35. Plus 1/2 of 5 squared, that's going to be 12.5. 343.35 plus 12.5 is 355.85. You got a couple of options here. We got to get rid of the half. We can either divide by 1/2, or what's another thing that we can do to get rid of the 1/2? Divide by 1/2 or times it by 2. Yeah, divide by 1/2, times it by 2. Doesn't really matter which one you do. Okay, whichever you do, you're going to end up with 711.7, I think, equals VF squared. And then we're going to square root that, and we should get, I don't know, maybe 26, 27 meters per second. Who's got a value for that? 26.67, or we'll just say 27.7 meters per second, right? Oh, sorry, 26.7. Somehow I'm rounding 26 point, rounding the wrong digit there. Good. Anybody have another way that we could have solved this problem with? a second way, not a better way, not a worse way, just a different way. Think back to your group B equations for a second. What would be the most obvious one to solve this question with? Given VI, given the acceleration is 9.81, given that you're looking for VF, you've got the height or the displacement that it falls. What else could you use? Yep. Yeah, you could use VF squared is equal to VI squared plus 2AD. I don't want you to use that today because I want you to get practice using this. Okay, but in the end, on a test, you know, if you do it right, I'll accept it. It's just that this can be used for more things than VF squared is equal to VI squared plus 2AD. So it's a little bit more versatile. That's why I want you to learn it. Real quickly, though, I want to show you something, just as a little aside. Okay, there's the other equation that could have been used to solve this. Okay, we didn't use it, but could have. Well, I'm going to take a look at this for a second. Okay, EI equals EF. We had MGH plus 1 half mv squared equals 1 half mv squared, and we canceled out one of the m's, right? In other words, you drop an object, it doesn't matter how heavy the object is, it's going to be moving at the same speed when it hits. We learned that back in Unit 1 because it accelerates at the same rate. Take this equation and let's go somewhere different with it. Let's actually rearrange this. Okay, we got GH initial plus 1 half V initial squared equals 1 half V final squared. Now you know that you can do whatever you want to a term here as long as you do it to every term. I can multiply each term by 16,112 or whatever I want as long as I do it to every term. I'm going to do something a little bit easier. I'm going to multiply every term by 2. 2GH initial plus VI squared. Now the half is gone because I multiplied it by 2 equals VF squared. Let's change the order of this a little bit and see what it looks like. VF squared is equal to VI squared plus 2GH initial. What's G? Yeah, my acceleration. What's the initial height? It's the same as my displacement, right? So really, in this situation, in this case, aren't I doing exactly the same thing? Really, I used VF squared is equal to VI squared plus 2AD. I just didn't know it when I was doing it. The reality is, guys, back in Unit 1, when we used this equation, it came from the law of conservation of mechanical energy. We just didn't tell you that because you didn't know anything about energy at that point. Okay, again, go with this today, at least because it's a method that you've got to learn to solve some problems. Okay, but in the end, on a test, if this one will work, go ahead and try it. Got another example for you. 6.9 on 313. Here's a roller coaster. Okay, here's a roller coaster this time. It's not going straight down, or at least hopefully not going straight down. We got a roller coaster that has a mass of 800 kilograms. One point on its journey, it's 4.0 meters per second. And it's 35 meters above the ground. Later, its speed is 20 meters per second. So it's like this. Here's my roller coaster that has a mass of 800 kilograms and a speed of 4 meters per second. It's going down a hill, right? Because it's speeding up. Its speed right here is 20 meters per second. We want to find the initial mechanical energy, and we want to find the potential energy at the end. Now, it says that it's moving at 4 meters per second when it's 35 meters above the ground. We're not told what the height of the second one is, right? I drew that height down to the bottom there, but really I should draw it down to here, right? Maybe this car is on the ground at the second point, but we don't know that for sure. All right, so the last question we did, we said that the law of conservation of mechanical energy is applicable. We did that, but we said that VF squared is equal to VI squared plus 2AD also worked. It's a little bit harder to make kinematics equations work in this one. And that's why I want you to learn that tool that we're teaching you right now, conservation of energy. All right, here's our situation. We want to find the initial mechanical energy. Okay, let's do that. That's easy enough. The initial mechanical energy is the kinetic energy plus the potential energy at the beginning. So we're going to say it's, by the way, the m doesn't cancel here because it doesn't appear on the left side. Mass of 800 times VI is 4 squared plus 800 times 9.81 times 35. Figure out what that is. 0.5 times 800 times 4 squared. Let's add to that brackets 800 times 9.81 times 35. We get a total mechanical energy of 281,080. We're going to say that's 2.81 times 10 to the 5 joules. All right, good. Initial mechanical energy, kinetic and potential energy. Hey, what do we know, first of all, about the mechanical energy at the second point? What if question B didn't say, what's the potential energy at the second instance? What if it said, what's the mechanical energy at the second instance? What would the answer be? Quick. Lightning fast answer for this. Julia? It'd be the same, right? There's a question on your field trip assignment that's like that. Basically, it says, here's the energy. You calculate the energy at the top, and then it's going to say, what's the energy at the bottom? And you're going to give me the exact same number. Okay, in the absence of friction, that total mechanical energy has to remain the same. Now, it's going to be more kinetic at the bottom and less potential, but the total will remain the same. Well, that's not what this question asks. It says, what's the gravitational potential energy in the second instance? All right, let's say this. EI equals EF. Let's say at the beginning, it's got potential energy because it's got a height, and it's got kinetic energy because it's moving. Well, let's say at the end, it's got potential energy as well because it's got a height. And let's say it's got kinetic energy because it's moving. Make sense? I'm going to simplify this a little bit, though. I'm just going to say for the left-hand side, I'm not going to cancel out m this time, even though I technically could. I'm going to leave it and just say the left side is 281,080 joules. Where did I get that from? I just calculated it, right? I just calculated it for the total mechanical energy at the beginning. Now, the final potential energy is mgh, but since I'm just looking for its value, let's just sub in the term for it, EP, plus 1/2 of the mass times VF squared. So the initial kinetic and potential energy combined equals the final kinetic and potential energy. I want to find the final potential. You see, for this question, it becomes a lot more difficult to use VF squared is equal to VI squared plus 2AD, even though ultimately it's the same thing. Let's calculate 0.5 times 800 times 20 squared. Let's say 281,080. Subtract that value. Gives me 121,080. Can you tell me why the potential energy at point B, the lowest point, is lower than the potential energy was at the top? Didn't I say energy has to stay the same? Why did potential energy go down as it went down the hill? That? Because kinetic energy went up and the total has to be the same. Does that make sense? Yes? All right. Here's what I'd like you to work on now for the next little while here, guys. It's going to be your last worksheet in that booklet, which is conservation of energy. I think it's number 4 or 5. It is worksheet number 5. Okay, work at your desks to that for a few minutes, and then we'll take a look at what we need to do in a moment. We've had a chance to work on these for a few minutes now. I want to take a look at question number 2 and make sure we're on the right track with these things. Number 2 says a ball is dropped from a height of 60 meters, a 60-meter high building, and it's going to fall to the ground, right? But we're not looking for how fast it's moving when it hits the ground. Rather, we're looking for how fast it's moving halfway down, like 30 meters before it strikes the ground. So we're going to say the initial height here is 60 meters. We're going to say the initial speed is 0 because it's dropped. So the initial kinetic energy, the initial speed would be 0. We've got the final height of 30 meters, and we're looking for the final speed here as it's 30 meters above the ground. We're going to say EI equals EF, even though in this case, that VF squared is equal to VI squared plus 2AD would definitely work. Yeah, I want to do EI equals EF. Now ask yourself, what kind of energy does this object have as it's dropped? Well, it's got potential, obviously, right? Because it's got a height. So we're going to say EI is mgh, initial. Is it moving as it's dropped? Is it moving as it's dropped? Now, it is after it's dropped, right? But is it moving as it's dropped? No, it's not, right? So the initial energy is just potential energy at this point. No kinetic energy, okay? Now, when it reaches the halfway point, does it still have a height? Does it still have a height? Yeah, it does. So we're going to call it mgh final. We've got potential energy at the end. Is it moving when it's gone halfway down, William? Yeah, it is. So we're going to say it's got kinetic energy. This is the way we're going to set this problem up. mgh initial equals mgh final plus 1f mvf squared. Okay? We got a potential energy in the beginning that's converted to kinetic energy. But by the time we get halfway down, not all of it is kinetic energy, only half of it is kinetic energy. So we still have some potential energy left. Now, a couple of you guys were asking me, well, what do we do with the mass here? We don't know what the mass is. I'll tell you what to do with the mass. David? Cross it out, cancel it, right? Here's in every term, let's cancel it. We know G is 9.81 meters per second squared. And the initial height is 60 equals 9.81 times 30 plus 1/2 of VF squared. We solve for VF, that works out to be 24.3 meters per second. Anybody do this slightly differently but still use conservation of energy? Anybody do this? You don't have to write down both solutions here. Both are valid. The way I'm about to show you is a little bit shorter, but I wouldn't suggest that it's easier. It might be a tiny bit harder, but I just want to expose you to it. If we said EI, this is for question number 2 again, EI equals EF. If we said the initial energy is all potential and the final energy is all kinetic, that can work. But how? How can that work? Okay, if we include final potential energy in the blue solution here, how can the green solution possibly give us the same answer? Remember what we said about potential energy when we started it? We have to have a reference point. You remember what we said about that reference point? It can be wherever we want. Where did we define my reference point here in the blue question? The ground. Where am I going to define my reference point here? Halfway down. If I define it halfway down, what's my initial height? If my 0 point is halfway to the ground, then my initial height will be what? How far am I above my 0 point? How far am I above halfway down when I start? 30 meters. So we could say HI is 30 meters, but if you do that, then you make HF 0. Because if my reference point is halfway down, then it's got to be halfway down for the whole problem. You solve for VF there, lo and behold, it works out to be 24.3 meters per second. So mathematically, this is definitely easier, but I don't think conceptually it's necessarily easier. Hey, whatever way works for you. Okay, whatever way works for you is the way that you should do it.